find equilibria and the stability as a function of R, plot the analytically expected bifurcation diagram, right? So I think here what happens is if R is less than 0, then you will have extinction equilibrium, which is stable. If R is greater than 0, you probably have X star is equal to 1 as the equilibrium, right? So you have extinction. After that, you have 1, and which remains stable up to some value of R. I don't know. Now I don't remember what's the value of small r at which the stability is lost. Okay, some people are saying, is my screen stuck? What do you mean by that? I'm not showing anything anyway. Hello, can you hear me? Okay, right now I'm not sharing any screen or anything. So I'm just, are you able to hear me? Can somebody confirm that you're able to hear me?
Yes, sir.
Yes, sir. Maybe you're thinking the screen is stuck primarily because I'm not showing really anything to you. Okay. I'm just going to the assignment. Okay. So any questions about the first question? So you must have been able to do this, right? Okay.
Sir?
Yeah.
I had a doubt regarding the bifurcation point. Like when we found it analytically, what we did is that we found where it changes from stable to unstable, right? By finding the logistical model. Yeah, logistic model or the recur model? Logistic model. Okay. We did df by dx is less than 1 for stability and greater than 1 for unstable. Yeah. But how do we know that that's where it bifurcates? As in bifurcation point is defined as the point when that modulus of f is equal to 1. Right, because at that point, the stability of the point equilibrium that you were investigating doesn't exist anymore, right? Sorry, sir, my internet disconnected for a moment. Can you just repeat what you said? So it's also possible that my internet may not be great today. I am at home. Okay. Although usually the internet at home is better than the one at office. So what I was basically saying was that when you, of course, your question is how do you connect between bifurcation point and the modulus of f prime? Is that your question? Yeah, how do you make that? That is my question. Yeah. So usually, let's say you have found the equilibrium, right? Okay, and you have found the region of parameter space where that equilibrium is valid as a valid solution. Okay, and then in that region of parameter space, find wherever f prime mod is equal to 1, right? Now and then you have some region of parameter space before and after where it was less than 1, after which it now becomes greater than 1, right? So this transition, what means the stability of the equilibrium that you are interested in changes at that point, right? Wherever the mod f became 1. Is that right? That means at that point, the stability of the equilibrium has changed, and that is the definition of bifurcation point. Could it not just be an inflection point where it points towards that in one direction and just goes like it's unstable in the other direction? So is it, I mean, it's asking a hypothetical question, is it? Is it actually possible that it goes to an inflection point and then comes back? Is that what you're asking? Okay. Yeah, that's what I don't know biologically how, but because it actually is in principle possible. I don't know of any places where it happened, but it's up, I can in principle construct some mathematical function where that might actually happen. Then it has the features of bifurcation at that point, but actually it goes back. It's in principle possible. So to really identify bifurcation point, you must plot the bifurcation diagram. All right. Okay. And to really see what's happening both before and after the parameter values at which f prime mod actually became equal to 1. Okay, that would be a sort of cleaner way of showing a bifurcation diagram. Also, just to be clear, bifurcation doesn't always mean a period doubling bifurcation, right? Bifurcation is change of stability. Okay, so in the logistic model, when 0 was the stable equilibrium between 0 and 1, right? And then it lost the stability beyond 1. whereas the finite equilibrium point now picks up the stability, right? So
Okay.
there was, that point is also a bifurcation point, right?
All right. Okay.
It's not always, bifurcation does not mean that things bifurcate the way it happens for the, period doubling. So all points where stability structure of the system changes, you call them bifurcation points.
So, and also the 2 points, or like the 2 points between which the period, in the period 2 cycle, the 2 points between which the population oscillates, do we define stability for them? Do we call them stable points because it comes back to them eventually?
Yeah, that's a good question. So if you now say, for example, to define equilibrium, define stability, you need an equilibrium value, right? And then you define stability, right? So equilibrium is defined by that condition that, X star is equal to f of X star in the case of discrete time population models, right?
Oh,
so
okay.
by the definition, period to cycle will not be a stable cycle. But you do raise a very interesting point. Okay, to address that question, let me share my screen. Why not generalize is your question, right? Where is my okay, here it is. Okay, are you able to see the screen?
Yes, sir.
Okay, so let's say, so you're asking now, technically even in a period 2 cycle, things do come back to the same point after two time periods, 2 generations, right? In a four period cycle, you do come back to the same point after 4 generations, right? And so on. So now it is coming back. Why can't you describe something like stability? Is a very valid question to ask. So indeed, mathematically you can. There's nothing really that stops you from doing so. So how did we define stability? We said xt is equal to f of xt is our equation, and the equilibrium we defined it in the following way. Is that right? Equilibrium is when across consecutive generations population size doesn't change. Okay. Oh, sorry, this is a +1 on the left hand side. Okay. Now let us look at xt plus 2. What is this? This is f of x of t plus 1, right? Now what is x of t plus 1? That I can use the equation above. So I can write this as f of xt. Is that right? So basically x of t plus 2 is equal to f of xt. Is that correct? I hope all of you understand what this notation means, right? And then now if I can write f of xt as a new function g of xt, I can actually connect between tth generation and the t plus 2nd generation. Is that right? So now I can actually define a sort of equilibrium across 2 generations. This is a new type of equilibrium. What does it mean? That xt plus 2 is equal to x star is equal to g of x star. What this means is that xt plus 2 is same as xt. Okay. Isn't this same as the period 2 cycle? Xt plus 2 is equal to xt, right? So now if I use this condition, then by solving x star is equal to g of x star, I now have a new discrete time model where I sort of try to predict population across 2 generations, and one can define equilibrium across 2 generations without worrying what happens in between. And now by solving this, I get the equilibrium again. I can actually solve the stability of this again, right? Instead of f, now I have g. Okay, so you're right. Your question is really great because we can indeed generalize, at least mathematically, the idea of equilibrium for a single generation to even cycles. So now I can generalize it to any n cycle, right? It could be the same as a period 3 cycle. Then I can define xt plus 3 is equal to a new function h of x, which is h of x is given by f applied to itself 3 times. Okay, And then now we can therefore calculate the equilibrium again. Okay, it's actually, if you look at chapter 10 of Strogatz, which I have recommended you to read, if you're interested in more mathematical sort of understanding, these points are actually covered there. You can actually, using this method, you can also find the stability of the period to cycle. So once the period to, so in this transformed model, it's a mathematical transformation, right? In this transformed model, the stability of this equation is a stable equilibrium of this equation will be actually period to cycles. Okay, and I mean, for those who are interested in mathematical aspects, I would strongly recommend solving this and finding it out. Actually, you will get some really sort of elegant solutions. You can even find the region of parameter space where period to cycle is stable, and so on. Okay. So any more questions on the assignment? Let me open the assignment again. That was the first question. And then I had asked, I do want to quickly discuss the next two questions. Okay. But I hope that the first question was basically whatever you have learned so far, you are asked to apply from one model to another model. Okay, that makes sense, right? I hope you were able to get all of this. And the second question, okay, let's look at the second question. I asked you, for each stability regime of either logistic or the recurrent model, generate a time series with a suitable initial condition and plot x of t plus 1 versus xt. What do you infer from such a graph? What did you find? I hope this question was interesting to solve in some ways. Okay, so I hope you all found something on these lines. So imagine let's plot the bifurcation diagram for the logistic model, right? R0 x star, you would have found something like this, right? 0 up to 1, and then you have finite population size up to 2, which then bifurcates into 2, and then more bifurcations. Okay, and I had also posted the complete bifurcation diagram, and I had also posted the link, right, to how to generate the complete bifurcation diagram. I had actually posted a R code, right? I hope you were able to use that and generate much more complex, and I hope that you also played around zooming in what's all happening here, right? Okay, so now let's look at let's not even worry about this between 0 and 1, because things go extinct, you can't really do much with it. Let's look at what happens between 1 and 3. Between 1 and 3, what happens if you start anywhere in this region, you just sort of reach this equilibrium point, right? For a given value of R, you basically reach this equilibrium point that was given by R0 minus 1 divided by R0. So how does that time series usually look like? If you were to plot xt versus t, if you began very close to the equilibrium value, you would reach like this. If you began far away, it would reach like this. Sometimes there may even be small oscillations depending on the value of R0. Is that right? Now from this, if you were to plot xt on the x-axis and xt plus 1 on the y-axis, what did you find? I think you may have found something like this. Is that right? To a large part. I would have found some 2-3 points and then some clusters like this. Is that right?
Oh, yes.
This is for R less than 3.
So stable.
And let's say now you do this for xt versus t for some cyclical behavior. Okay, here what will you find? You probably would have found, again, exactly depending on the initial conditions, maybe something like this, a small cluster here, and this might be a small cluster. Is that right? For period to cycle region?
Yes. Yep.
Okay. And now if we had period 4, well, this is a bad graph, okay? Please excuse me. You would have found something like this, right? This is period 4. This is 2 cycle, 4 cycle. And this is equilibrium. This is what you found, by the way. I mean, of course, it might, the exact nature you will get. Okay, so what can you infer from this so far? by these kind of plots are called return maps, by the way. I think I know I've forgotten a bit of this, but maybe I think it's called point K return maps. So this is how it looks. Okay. Now, if you do for chaotic regime, what do you find?
It
Did you
goes
try in the
for,
chaotic region?
Better arc.
yeah, the
Get
whole
a much
parabola.
better arc, right?
Yeah.
Okay. That's your question number 2 that I had. And then I had also asked, what do you infer from such a graph? I don't know what you answered. I'm curious to see. Okay. So, so depending on the parameter regime you are, now that you have seen all of this, maybe you can make some infer. If you found a single cluster, maybe you can infer that you are in a. See, of course, in real data, if you think about real data, it will not be exactly a perfect cycle that oscillates between two precise mathematical precise points, right? There will be some small fluctuations around it. So what you see is not a single point here, but maybe a cluster here, right? A sort of cloud here. So if you find one cloud, you can say you are fluctuating around a stable equilibrium. If you are fluctuating between two clouds, what can you say? You may be able to infer that you are in a two-cycle regime. And likewise, to find n sort of distinctly identifiable clouds, you can say maybe you are in that n cycle. On the other hand, if you had a much nicer arc, what can you conclude?
Chaotic region.
You are in a chaotic region, right? Does it make sense? Okay. This is very interesting, right? To make these inferences, I don't need to know the model, right? Right. And also, I want, okay, does it make sense? You don't need to know the model. If we had done with this with recurrent population model, would you have found the same results instead of logistic? Okay, so if you actually manage to do both, you would have found that the results, will be same for both the models. So the conclusions you are drawing here is not specific to recurrent, logistic model alone. Okay, so by plotting these return maps, you can make some inference about the nature of the dynamics of the system, the system that you are studying actually exhibits. Okay, so that was the second question. So the third question, any questions before I move forward?
Yeah, I have a question.
Yeah.
So, in these return maps, depending on number of clusters, you can tell which limit cycle it is in, right?
That's one. Yeah.
For
Yeah, of
chaotic-
course, it depends on how distinct cluster they are.
Yeah. So for chaotic behavior, can you say that it's in a way an infinite order limit cycle? Because
Absolutely, you're absolutely right. Yes, in fact, so yeah, in this logistic model, right? You find this, 2, 4, 8, 16, and so on, right? The 2 power n cycles are there, right? And then keeps on increasing, and when n goes to infinity, you do get a, you do get a chaotic orbit. Yeah.
Okay.
So basically, infinitely large periodic cycle is, has all the properties of a chaotic orbit.
Okay.
Yeah, it's a very good point.
Sir, I have a question. This is more related to the first one. I would like to know from which period cycle does the chaotic regime actually start? After period 8 cycle or after period 16? Do we have some demarcation like that?
It's technically only at the infinitely large period cycle.
Since in the first question we were supposed to write at what R naught value the chaotic part happens. So,
In the first question. Okay. In the first question. Yeah, okay. I see your point. Yeah. How do you answer that question without knowing this? Is that what you're saying?
yes. Since in part B you mentioned period 8 cycle, I've taken that as the
period 8 cycle is not chaotic, by the way.
yes.
Period 8 cycle is period
after
8.
period 8. I've taken it as after period 8 chaotic for
So
that.
so yeah, I don't know how many of you noticed this. The distance between period doubling bifurcations dramatically reduces. It sort of reduces geometrically. Okay.
Yes,
So it's actually a geometric series, reducing geometric series. So you reach that point fairly quickly.
okay.
For example, even in the logistic model, 0.45 is the region where you find period 2, and I think it's 0.09 for period 8, period 4, and then it reduces geometrically by a fraction of 4 point something for every subsequent. So by a factor of 4, I think, or even more, I think, if I'm right.
But
Roughly around
also,
point.
but also with increase in R, there are some regions of R, some range of R when it again comes back to period 2 or period 4, and then
Absolutely,
again.
yes, absolutely. It's a mess between, in that entire region between 3.6 and 4 in logistic model. It's a huge mess. You get everything. You actually get there are mathematical theorems that prove that you actually have every integer periodic cycle. Okay, not just 2 power n, but actually every integer periodic cycle. And R0 is equal to 4 also corresponds to chaos in this specific case. But but as long as you get reasonable values, also when I say find value of small r where you find chaos. So I'm not asking you to just write a number. I'm hoping that you have actually tested for yourself whether it actually shows chaos. So how do you do that? We discussed in the one of the class homework, right? A lab assignment. You plot ET as a function of t, and
Yes,
where
sir.
ET was defined as the difference between two trajectories as a function of time. And although you start with a very, very small difference between the two, that difference must grow with time. That's when, so you can make a reasonable guess of what R is, but you must make sure that you test that time series, ET time series, the error between two trajectories, which are very, very close to start off with. If they diverge over time, if they become basically sort of, effectively independent by visual inspection, you can conclude they are chaos. Of course, there are more formal way of doing it, which I haven't covered in the class. Therefore, I don't expect that you will do them in assignment.
And also, we had a question where you asked which logistic versus Ricker, which is better for biological, which is biologically realistic. But that depends on the biological system we are studying, right?
Yeah. So there's no one answer to that. So you pick, as long as you provide right justification, it's fine.
Okay. Thank you.
But usually there is a tendency to sort of pick Ricker over logistic, primarily because of this weird feature of logistic model that if when R0 is greater than 4, you have a negative value of X population density, and when X, when X goes greater than K, right, we have the same problem again, right? So for that reason, and since we have no easy way of parameterizing those two, people often prefer Ricker population model.
Thank you.
Sort of biologically, for biological experiments and verifications. Okay, but that doesn't mean you have to choose that answer. As long as you have given valid reasons for your choice, that's totally fine. Okay, so now the third question is basically in such an extension of second question. I wanted them to be separate, that way you sort of it's very clear to you. Now to construct f, what is the I asked the question, under what conditions does a construction of the function f is feasible? I think if you look at these graphs, the answer is there, right? So can you construct the function f if the population was hovering around stable equilibrium? So you'll only get this small cloud around the equilibrium, so therefore not possible. If it was in a cyclical orbit with small number of cycles, again it's unlikely. So maybe it was in a cycle with a large cycle, let's say period 128 cycle or period 100 cycle. It's then in principle possible that because it is jumping back and forth between so many values, you may get a idea of the function. Okay, so if you can pick the periodic or sort of regime, periodicity regime, as long as you have picked a large cycle. Okay, there you should be able to construct f. And then when you are in the chaotic region, can you construct again? And in fact, yes, to be able to construct the model from data, the best bet is when the system is actually in a chaotic regime.
Sir, but if it is chaotic, how I don't understand how it will be more easier to construct the model, like.
So isn't that what you found in your previous question? In your previous question number 2, isn't that what you actually found? If you plot xt plus 1 versus xt, okay. So in question number 3, I'm not telling you how will you construct f. One thing, I don't know how many of you noticed when you were solving 2, by the way, if you plot xt plus 1 versus xt, what is the expected graph, by the way? Since xt plus 1 is nothing but f of xt, to construct f of xt, you just can plot xt plus 1 versus xt, right? Is that right?
Yeah.
Is that right? So that's the first connection you had to make for question number 3. So to construct f of xt, you just have to plot return maps. Okay. And then what you need to do, you now have to, but as we know from question number 2, not every sort of, stability regime will yield you large enough data points to construct f. In the stable equilibrium regime, you have only one cloud around the equilibrium. In period 2 regime, you will have 2 clouds around the, two population densities. But only in the chaotic regime, you actually get a much larger coverage, right? And that is when you can make reasonable inferences about where, the function f. So that was what I was expecting for your question number 3. Did you have any other answers?
Sir,
Does my answer make sense?
Yes. Regarding last lab, you uploaded a presentation in which you mentioned that long-term experiments generally don't give feasible constructs of functions. Can you
May not.
elaborate?
I said may not. No?
Yes,
May
yes.
not.
Generally, okay. Yeah, may not give.
I don't know what exactly I wrote, but I just mentioned they may not. I may not have. I don't know what exactly I wrote, but that was the intention. Yeah.
Vishu,
Go ahead. What's your question, by the way? Can you please?
No, what do you
question?
exactly mean by that?
So basically, imagine a population in stable equilibrium, but imagine I have 1,000 generations data. How will the xt plus 1 versus xt look like?
Oh yeah, it'll get clustered
be,
onto one point. Yes.
Yeah, right. So just because you have a long-term data doesn't guarantee you the construction of this layer f. Let's call this growth function. Okay. Only when you have a chaotic regime, the long-term data can actually help you construct f. Right.
Vishu, does it have to be chaotic, or can we say like when the population is growing or declining due to environmental perturbations or pressures or anything, be it the scientist?
As long as you have picked that answer, I'm totally fine with it. It's actually possible that you are in a stable equilibrium, but if the environmental stochasticity is very high, in such a case also you should be able to construct f of xt.
I don't mean it's in equilibrium. I don't mean it's in equilibrium. I don't know if it's chaotic or not. That I don't know. All I know is it's not in an equilibrium. There is some growth or some decline. If that's what we call chaos, fine, so be it. I just mean like the population is growing sometimes, declining other times.
Why would it do on its own though?
Due to environmental perturbations. That's what I mean.
Okay.
Like, or the scientist herself doing it, but either of the two.
Okay. So yeah, you can manipulate the system to sort of, forcibly ask it to decline or forcibly increase, and observe those trajectories. That will also help you construct. Yeah. In fact, I have given you a small question to think in that PowerPoint I have uploaded, the Google Slides I have uploaded. But I didn't give you the answer intentionally. But there is some experimental manipulations you can do to construct. But here the question 3 was more about if somebody has given you data, under what conditions can you reasonably, and if assuming that a discrete population model governing is given by NT plus 1 is equal to f of NT actually is an accurate description. That's what I'm saying. No, assuming it indeed follows a discrete time dynamics given by f of NT is equal to f of NT. Under this assumption, the answer is that only chaotic regime or a very high periodicity regime, only those two can yield you a construction of f. Does that make sense?
Yeah.
But it's possible that under other conditions you can do. But given this setup I have given you for question number 3, chaotic or high periodicity is the correct answer. But if I don't mind if you have deviated from my assumptions a bit, as long as you have made it clear how you plan to do. Okay. For example, you have said that, hey, look, it's okay that I can assume this is a good model, but I know there will always be stochasticity in the real world data of various types. Therefore, I will also observe periods of growth and decay entirely internally. In such a case also, I should be able to construct f. As long as you have given this argument, I am fine with it.
Okay, great. Yeah.
Okay. So it was question number 3. And then question number 4, I won't discuss anything right now because I don't know what you have written. Okay. So I will try to go through it, and if there is anything interesting people have said, I will discuss in one of the later classes. Is that fine? Okay. So now, if there are no more questions, let's continue. So sort of where we left on Wednesday. Okay. So can I continue? No more questions, right, on the assignment? Okay, thank you. So let's now go back to continuous time. Okay, so we wrote the general form of model in this form, dn by dt, wherein is the population density, population size is of this form, f of n. Okay, and we find equilibrium by setting dn by dt is equal to 0, meaning the population doesn't change anymore. So population doesn't change is same as saying the derivative of n with time is 0. And then if that value is n star, then so that means f of n has to be 0 at that value of n. And we find the values of equilibrium by solving this equation. F of n star is equal to 0. Okay. Now how do we find stability? We calculate the derivative of this function, the growth rate function, at the equilibrium, and then we check if it is less than 0. If it is indeed less than 0, we say it's a stable equilibrium. If it is greater than 0, we say it's unstable equilibrium. And again, remember the stability is defined for small perturbations, because in our derivation, we ignored all the higher order terms in the Taylor series, right? So we only looked at first order term, which is valid only if the perturbations we make are really small. Okay, and therefore this analysis is also called linear stability analysis. Oh, linear. And it's also called local stability because we're only looking at small perturbations. So linear comes from the word linear comes from the fact that in the Taylor series we retain only the linear term. Local comes from the fact that we are making a small perturbation around the equilibrium. Okay, so this is how we find equilibrium and stability. Now let us apply this to the logistic population model, continuous time logistic population model. So dn by dt was r0n times 1 minus n over k. So here too you can do the same rescaling, by the way. So just learn that technique, always see if you can eliminate, and that's always very helpful. So let's define x as n by k, and if you do that, you must be able to verify that you will get the simpler equation. Okay. So remember that in this model, R0 can take values theoretically between minus infinity and plus infinity. There is absolutely no restriction on the values of R0. And likewise, there is, of course, there will be biological limits placed, which is, the maximum birth rate. Okay. And again, X has technically no limits. Of course, it has to be greater than or equal to less, 0. X cannot be a negative value because then it loses the meaning of population density if it's negative. Okay, so this is the equation we have. So now how do we find equilibrium? We set f of x equal to 0. What is f? For this model, f of x will be r0x into 1 minus x. So equilibrium we set by f of x equal to 0, and therefore, okay, So that can happen either when x star itself is 0 or x star is equal to 1. Note that x star is equal to 1 is same as saying n is equal to k. Okay. So we have two equilibrium for this model. Okay. Now, how do we find stability? So to find stability, we need to find f prime of x, that is basically d by dx of r0x into 1 minus x, that is basically r0 times 2 r0x. Is it fine? Now, what is f prime of x star is equal to 0? That is basically minus 2 r0x. I hope I've made no mistakes. Is that correct?
It's R0, sir.
It's R0, right?
Oh, right. I've already found. Oh, I don't know what it is. Okay, sorry. It's just R0. Okay. So the f prime at x star is equal to 0 is R0. And remember, what's the interpretation of f prime x star? F prime x star basically is the per capita growth rate of the perturbation. So remember, so when the per capita growth rate is positive, there will be an increase. And when the per capita growth rate is negative, there will be a decrease. Always remember this, right? So therefore, now if we want the stability of the equilibrium x star is equal to 0, this means that R has to be stable if its per capita growth rate is negative. Is that fine? And it's unstable, just 1 second, if R0 is positive. Okay, go ahead, please.
You mentioned about like the it's per capita growth rate of the perturbation. So
Yeah.
what exactly are you perturbing here?
So there is an equilibrium value x star. Okay. And then to that, there is some population density which is equilibrium. Let's say it might be 100 individuals per kilometer square. Okay. Now, what does a small perturbation to it mean? I will add a few individuals to it. That's the one perturbation. Alternatively, I remove a few individuals from that equilibrium. That's another perturbation one can do. So perturbation means from the equilibrium either increase or decrease, but only by a little bit. Now, if the equilibrium is 0, I can only make an addition. I cannot make a further decrease, right? That will not be biologically meaningful. So for an extinction equilibrium, to find stability, it's like adding a few individuals. If the extinction equilibrium is stable, the ones that you have added will now die off. Does that make sense?
Yes, sir.
Okay. So that means that, in the logistic model, x star is equal to 0 is stable for R0 negative, and it is unstable for R0 positive. Okay. Now let's also look at x star is equal to 1, which corresponds to k, right? Where n corresponds to k. What is the value there? It will be R0 minus 2R times 1. What will that be? So I'm basically plugging in x is equal to 1 in this equation. Okay. I will get minus R0. Is that fine? Look at the contrast here, right? For the x star is equal to 0 equilibrium, and for the x star is equal to 1 equilibrium, it's basically the negative of each other, right? Which basically means that the stability criterion are basically swapped. Is stable if R0 is positive. Okay. Is unstable if R0 is negative. Does that make sense? Is that clear?
Yes, sir.
Okay. So let us do the same thing we have done in the past, which is bifurcation diagram. Okay. Okay, so what do we find? For values of R0 less than 0, 0 is the stable equilibrium. Is it right? And then 0 becomes unstable.
Sir, I have a doubt.
Yeah.
So at x star equals 1 for negative r naught, you still have an equilibrium point, right? But how does that make sense? Because you have birth rate lesser than death rate. Biologically, like it should reduce as soon as.
Say that again. Go back.
So if you start with x star equals 1 and you have negative r naught.
R naught is not negative. Oh, okay. You are starting with x star is equal to 1 and you have a negative
Yes.
R naught. Okay.
Yeah,
Fine. Yeah.
it's still an equilibrium point, but biologically that doesn't make sense, right? Because birth rate is lesser than death rate.
So if you are at the equilibrium, because the growth rate itself is 0, right? See, at the equilibrium, okay, you're saying what is the biology that is actually maintaining it at a high value, despite the fact that R0 is negative. Okay, it's actually a good question. I haven't thought about this. Does everyone understand this question, by the way? So his question is that, let's imagine that the 100 population size was the, corresponds to, n is equal to k. Okay, that's the carrying. So k in this model, by the way, actually can be interpreted as carrying capacity. Okay. So k in this model can be interpreted as carrying capacity. Okay. So the question that, who asked this question, by the way?
Sharaj.
Sharaj, yeah. Okay. So how do you interpret? So consider the case when I'm at this x star is equal to 1 equilibrium, but R0 is actually negative. Okay. Yeah, that's actually a very good question. So it turns out, okay, now there is unfortunately no easy answer I can give you. Okay. So in this sense, this model has a very funny feature. I will just tell you what it is. Basically, you are asking a question. I'm going to tell you even more bizarre thing. And that also cannot be explained. Okay. And that hopefully will explain you why there is actually a problem with this model too. Not just like the discrete time logistic model had a problem. This model also has a very funny problem. Okay. To do that, we have to learn a technique. But so before I go that, is everyone fine with what I have written so far, by the way? Is this fine? For R0 negative, we have only extinction equilibrium. Okay. For R0 positive, we have a unstable extinction equilibrium, but a stable carrying capacity equilibrium. Okay. This corresponds to carrying capacity. And it is stable in the sense that if I were to increase above this, system will come back to this. If I decrease, it will come back to this. Okay. If I am at 0 and if I make a perturbation, it will also again go there. Likewise, that's true for all values of R0. Which are positive. Okay. And on the other hand, if
it won't be carrying capacity, right? It will be x star equal to 1.
Exactly. Yeah. And in terms of the n, it actually is same as n is equal to k. Right?
Right.
Yeah. So is this fine so far to everyone? And does this also look like a recur discrete time model?
Yes, sir.
Yes.
Except that for a recur discrete time model, when R is greater than 2, if I am right, you have a period doubling bifurcation, right?
Correct.
Is R equal to 2? Okay. Yeah. But here, and again, in the discrete time recur model, this becomes unstable after R is equal to 2, right? Analytical calculations do not tell you what happens after that. It just tells you it becomes unstable after R is equal to greater than 2. But here, that's not the case. It's stable for all values of R. Right? So this curve extends forever.
Like, I have a doubt.
Yeah.
with respect to what Sharad had asked, if it's at like x star equals 1, and then you just give a small perturbation such that it goes to a negative R0 value, shouldn't it just
no,
go to
hold
the
on. The
other?
perturbation is in the population density, not in the value of R0.
Oh, okay.
See, perturbation is always to the state variable, right? In that, if you remember the derivation that I did in the last week's class, we consider n is equal to n star plus a perturbation, right? So perturbation is in the state variable, not in the parameter value.
So regarding Sharat's question, so like the question was saying if R naught is negative,
yeah,
it's somehow it's equilibrium, but then like death rate. So you say, but then like I was thinking the other way. See, the actual birth rate minus B minus D is R naught times 1 minus X, right?
Yeah.
So like if X is
it's
1,
not the actual birth, it's a total birth rate. I mean, total birth minus death rate. Yeah.
So that will be 0 only, right? So B minus B equals D, right? So I didn't quite understand what.
So of course, it has to be true. But I think intuitively, it's still there is a. You're right. Basically what you're saying is that don't just look at per capita, growth rate, which is indeed negative, right? Because R0 is negative. But if you look at the fact that the total population change, that will be x into 1 minus x. Okay. Okay. So now, and that actually will be 0. That's what you're basically saying, right?
Yes, sir.
That's fine. That's a mathematical argument. One should just think of it a bit more biologically. Let me just to sort of show that we are actually, when R is negative and when you are approaching this population sizes, actually something really bizarre happens. To understand that, we need to learn a method called graphical analysis. So far, what have we learned? We have learned mathematical analysis of equilibrium and stability, right? Which is, if I have given you an equation, x dot is equal to f of x, how will you find equilibrium and how will you find stability? Now let us do it in a slightly different way. So let's say I have again given you an equation of this form. How will you find equilibrium? Let us basically convert the mathematical conditions we have been thinking, and let us think them in a graphical way. Okay. So let me do that in the next page. Okay. So how do I do that? So let's plot f as a function of x. I don't like this color. Let's plot x on the y-axis, which is population density. Y-axis f. What is f? F is the population growth rate. Okay. So for the logistic model, how will this look like? For the logistic model, f is equal to R0 x into 1 minus x, right? Let's assume r greater than 0 for the time being. How will this now look like?
A
It will be
parabola.
a parabola, right? It starts at 0. So at x equal to 0, f is 0. And at x equal to 1, it's again 0. And it's x into 1 minus x in between, which is a symmetric parabola. Very symmetric, where the maximum occurs at half. Okay. And then for x greater than 1, this becomes negative. Therefore, the f becomes negative. Is that fine? There is really bad drawing here. Okay. There are no inflection points and so on. So, but it's just really my bad drawing. It's just a smooth curve around 1. So now,
sir,
yeah.
I have a question.
Yes, Ambarish.
From this particular diagram. So the total growth rate is maximum when x is very close to 0.
Is that really so? Total growth rate is 0 when you are close to 0, right?
No, I mean just after it crosses 0, the total growth rate is maximum, right?
So where is it maximum? Wherever f is maximum, right? Do you agree? This total growth rate is maximum when f is maximum. And when is it maximum? When x into 1 minus x is maximum, and the maximum value of x into 1 minus x is 1 by 4 when x equal to half. So this is when it is maximum. Okay, that's maximum. So population growth rate is maximum at half the carrying capacity. Okay, let's move on now. So I have plotted this for r 0 greater than 0. Okay, so how do we find equilibrium from such a graph? Equilibrium corresponds to f is equal to 0, right? F of x equal to 0, right? So what are the points on this graph where f is becoming 0? It's actually 0, right? And 1. Is that right? So there are two equilibrium values. So by plotting f as a function of the population density, you can find all the equilibrium by looking at wherever f intersects x-axis. Okay, so these are the equilibrium points now. Now, how do we find stability? Think about it again. It's a very simple way of doing it. Okay, one is, of course, you can look at the slope at these points, but let's do something more intuitive. Let's say this is the equilibrium. I may now made a perturbation. So 0 was the equilibrium, and I made a perturbation and added a few individuals. Therefore, now the population density x is now greater than 0. What is the growth rate here? It's positive. When the growth rate is positive, what happens to x? X has to increase. So let us write an arrow like this. Is everyone clear about what I have just done now? There was an equilibrium population at 0. I made a perturbation to this point. I have added a few individuals to this population. And now what happens to the growth rate? It's actually positive now. So therefore, the population size will now increase. Therefore, to represent it, I have added an arrow here. And then what happens is the population now comes to this population value. What's the growth rate again? It's again positive, right? I can therefore add another arrow indicating that the population is increasing. Between 0 and 1, how will the arrows look like? Will they all be in the same direction towards the right? Do you agree?
Yes, sir.
Right, because it's positive throughout, right? But that's not really our interest. We wanted to know what happens if we make a small perturbation to 0. What happened to small perturbation? It increased, right? That means the perturbation is going away from the original equilibrium. Therefore, 0 has to be an unstable equilibrium. Do you agree with that? Oh, I don't know what happened. Oh, okay. So unstable equilibrium, what we usually do is we denote it by a open circle. Okay. And now let's look at what happens when I'm near 1. So 1 is the another equilibrium. Let's say I make a perturbation to the left, meaning I reduce a few individuals from this population. I kill off a few individuals. Now the population is now at this stage, at this, at a value less than carrying capacity. What's the growth rate now? It's actually
Still positive.
Positive. So therefore I should do a right arrow. Let's say if I made a perturbation to this point, what would I have gotten? Again, it's positive. It's again to this direction. If I made a smaller perturbation, it's again this. That means every perturbation on the left side of this equilibrium is bringing back the population back to its equilibrium. Okay. Any reduction will be compensated. And biological reason for this is that when I have reduced the population size, the competition reduces, the intraspecific competition has reduced. Therefore now there is a actually increase in growth rate of the population. Therefore, the population will increase. Now, what happens if I made an opposite perturbation, which is I add a few individuals to this population? What's the growth rate now? It's actually negative. Therefore, will the population increase or decrease? It will actually decrease, right? Likewise, if I made a perturbation to this, what's going to happen? It would have again decreased. Again, same here. Okay. So we can use this graphical method to actually identify who is stable, who is unstable. So this equilibrium is an unstable equilibrium because the perturbation increased in size. Whereas from this point, from this equilibrium, perturbations I made decayed. Therefore, this is a stable equilibrium, and you typically denote them by solid circles. Okay. So I don't have to calculate any derivatives. I can just calculate the roots, and then by doing this graphical analysis, we know which is stable, which is unstable equilibrium. Okay, is everyone fine with this? So 0 is...
When we were doing it previously, did we find x star equal to 0 to be a stable equilibrium? Like when we did it mathematically?
So let's go back. So x star is equal to 0 is stable if R0 was negative. It's unstable if R0 was positive. Okay, so what did I plot? I was plotting R0 positive, right?
Right.
So it's consistent. Okay, and likewise, on the other hand, x is stable. Is that fine?
Yeah, got it.
Okay, excellent. And this will be true for all values of R0. How will this function change when you change R0? This function will look like even steeper like this when R0 is large. Oh God, I don't know why it became so thick. We will reduce it even further. And it will be like this for smaller values of R0. Okay. So for all values of R0, the functional form remains same. Therefore, the arrows I have drawn will not change. Okay. So how do I change? Oh, I actually switched to a marker over there. Okay. So this is how you can use the graphical methods to identify whether an equilibrium is stable or unstable. Okay. Now let's do the other case, which is R0 is negative. So what happens to f in that case? How will the f look like now?
Downward facing hyperbola. I mean parabola.
It actually will be an upward facing.
Exactly. Oh yeah, sorry.
Yeah. Yeah, but I think I understood what you meant. You meant this only, right? Yeah. So this is how it will look like.
Yeah.
1 and this is 0. Okay. When r is equal to r is less than 0. Is that fine, everyone? Because when r is less than 0, basically take the exact same value. If r is negative, whatever was positive here must become negative, right? It basically will now become a mirror image of this graph here. Is that right? Now again, what are the equilibrium? There are two equilibrium, one here and one here. Okay. Let's find the stability now. At R0, what's going to happen if I make a perturbation? If I add a few individuals to an extinct island or a barren island here, what's the growth rate? It's negative. So therefore, population will die off to 0. Is that fine? So this now is a stable equilibrium. On the other hand, imagine a population was at x equal to 1, another equilibrium. If I now reduce the population, what happens? It's again a negative growth rate. Okay. Therefore, the arrow will be leftwards. Okay. It comes here. Again, it's a negative growth rate. Therefore, the arrow will be leftwards. Basically, it will just push you to the extinction. So any perturbation from this equilibrium, x equal to 1, will lead to an extinction if the perturbation was to the left side. And that does make biological sense, right? Right? Does it make biological sense? Now, let's say from this equilibrium, if I now make a positive perturbation, if I add a few more individuals, what happens according to this?
It should go towards infinity, right?
So it now has a positive growth rate, right? Technically, according to this graph, right? So therefore, this arrow is in this direction. That means the perturbation I have made will now increase and come here. It's again positive. It increases. Okay. Let's use a red pen here. Okay. Does it make sense? You have a negative per capita growth rate, right? Even when population size is very, very small, right? We have the deaths are more than births. But if I am somehow magically increasing this population above carrying capacity, what happens? We have a positive growth rate. Does it make sense at all?
Doesn't seem to.
It doesn't make sense. So basically, this model should never be used when in this regime.
Isn't it same for the Ricker model? Even for Ricker model, we see that
Exact same problem.
like increase my starting point greater than 1, that is carrying capacity. And if the growth rate is negative, it will go to infinity.
Okay, yeah, same problem probably happens there also, right? I haven't studied Ricker model as in detail, but I guess because you're right, exactly same thing happens because R is negative. So instead of yeah, absolutely, yes. If you start with x greater than 1, the negative becomes positive. It has the exact same problem. Okay. So if R is less than 0, you must strictly work with x less than 1 regime. Okay. And if okay, so otherwise we'll get weird results. So another way of saying is, I'm not going to say don't work. This makes no sense. Therefore, don't study this model beyond this. This is a prohibited region. Okay. So that's why, it's important to understand every model will have such mathematical weirdness. We need to make sure when we are working with real sort of numbers, we never reach out, we never sort of exceed those, ranges. Okay. So, logistic discrete model had problems, right? As we just discovered, both the recurrent discrete model also has the same problem, and even the continuous time logistic model has the same problem. Okay, so of course people have discovered, use slightly more complex forms to avoid these kind of issues, but nevertheless, it's always possible that any model you write, we can have some weirdness, but make sure you don't enter those region of weirdness. Okay, mathematically it might still be okay, but biologically those values will have no meaning at all. Okay. So as long as you work within the acceptable regions, it's totally fine. Is that fine? But the graphical method is a very useful method to gain intuition of what's happening. Okay, and one can just plot the function for a given set of parameter values and get some intuition of what are all the equilibrium values, what are all the stable equilibrium, which are the unstable equilibrium, and so on. Any questions on this?
I have one general, like, comparing the discrete and the continuous model. In what ecological situations would you choose, say, the continuous over the discrete or the discrete over the continuous?
Yeah, so that relates to the last week's lab assignment also. So I would choose discrete when a non-overlapping generation is a reasonably good approximation. Otherwise, always stick to continuous time population models. Even better. See, technically, if you think of ecological population, let's think of bacterial growth dynamics. Okay, so how many individuals are there? There are probably 10 power 5 and above in any experiment, right? Maybe much more, right? Or think of tiger populations, right? In entire India, I mean that there were 10 power 6 individuals or more in a small beaker in your lab, right? Or petri dish lab. But if you think of tigers, all of India has around 3,000 individuals if we are very, very generous with the government estimates. Okay, so obviously the model you choose has to account for the numbers also. Okay, and this the densities that you're sort of really working with. Okay, so it's entire, for example, when very small populations are there, the discreteness of individuals becomes very important, and that can lead to a lot of additional sources of variations that these models will not capture. So in such a case, neither discrete time nor continuous time will work, because both of them have a common assumption, which is that both of them have a very common assumption, which I haven't discovered, which we haven't discussed much at all, by the way.
Migration.
But some people did, no, but what if I think of all of India as a single island, right? Maybe, or if I can think of the entire Central Indian landscape as an island, because we do know that there is no migration between Central Indian landscape and the Southern Indian tiger populations, right? So then maybe there can be. So it's not just an island or no migration. So no migration is important. But what's also important is the fact that the numbers you're dealing with. If the numbers are large, these models are fine because I can think of population density instead of population numbers. Okay, which means that I can deal with fractional numbers. It's not a big issue if I'm dealing with non-integer numbers in terms of densities. But the moment you have very small number of individuals, I'm now dealing with numbers like 10, 12, 13, 14, right? Those cannot be sort of converted to continuous numbers. Okay, and the moment you cannot do that means that the stochasticity associated with small numbers becomes very important. So both the models do not account for those kind of stochasticity. They're called demographic stochasticity. Okay, because the mean values do not make sense anymore. Okay, so so it really depends on the system you are really dealing with. So if the if you are working with a large population where isolated population is a good assumption, and if the non-overlapping generation is a good assumption, I will go with a discrete time model. However, if the generations are non-overlapping, then I would choose this model. But of course, remember that both of them have their own set of assumptions. No age structure, no demographic noise, no spatial distribution of individuals, right? So all those are ignored. If some of those become important, add those components to these models again. Okay. So at the end of the day, we must remember that the biological populations are discrete and the birth and death processes are stochastic. We have ignored both of them here. So if both of them can be ignored, these two model frameworks are fine. Okay. So now, having done this, now let's move to the let me now cover a couple of more points. Let's say now somebody does ask you, build a model. Okay, now which is sort of extension of Tarun's question now. Which one will you choose? Again, you have to revisit the set of assumptions you have made. Okay, and then try to see which is the right framework to use. Okay, broadly, as I mentioned, non-overlapping generation means discrete time framework is a reasonably good framework. If it's a continuous, sort of, population birth and death growth, and then in such a case, continuous time models are a better approximations. And if large population sizes are a reasonable assumption, again, these type of models are good. If we're going to deal with very small population sizes, we have to account for additional processes that happen. Okay, so now let us now stick to this framework, these two frameworks only, all else being equal, and let us again just think a few things, very important points while trying to build models. Always try to plot two graphs. Okay, so when you're trying to build a model, of let's say of this form. Okay, so first thing you would like to plot is this. I'll take that different color. Certainly plot this x versus f of x. Remember, what is f of x? It's the total population growth rate. And now ask, let's say we were doing intra-specific competition, right? If that was the dominant interaction in the population, we wanted to do a model of how total population growth rate will look like if intra-specific competition is the dominant force. Now, can you write this? Can you sort of guess how this function will look like? Of course, we now know that this kind of a quadratic function is a good approximation, but is that how we did the modeling, by the way? Is that how we arrived at a logistic model? No, we didn't do this, right? What we did was something different. What we did was not the total population growth rate. What we did was this, which is per capita growth rate. So we often have a much better intuition of per capita growth rate than the total population growth rate. See, this now makes much more sense. Now, if we think of competition as the driving factor, this per capita growth rate, this is just one, by the way. We understand this much better. So if per capita growth, if you think of intra-specific competition, right? Because we can say that, when the population density is very small, competition is least. So therefore, the per capita growth must be maximum, right? So I would start with the maximum value here, and then we can say when the population size is large, it becomes the per capita growth rate becomes small. Therefore, it must be a declining function, and in fact, maybe it might even become negative. Sorry, this is a bad graph, but I guess you got the point, right? So this is how we started the model. We wrote down how the per capita growth rate changes with population density. And we did this for the assumption of intraspecific, computation. Okay, so sometimes it turns out that writing or guessing what is the form of per capita growth rate is easier, but in some other cases this will be easier. So whenever I ask you, I will give you a new scenario. Okay, consider a population with this new biological process. Okay, now write down a model. You should try to think how both of these graphs look like. Okay, and then plot the graph, and then come up with a mathematical function that represents that graph, and then you write down the equation. Is that fine? So all of you understand the difference between these two, per capita growth rate and the total population growth rate. This is really, really important. This really helps us write down the mathematical models. Okay, now imagine this classic scenario, right? Resources were not a constraint, right? That means no competition. What will be the per capita growth rate? It will always be a constant, right? Okay. So therefore, this graph is actually quite useful. Another way of writing it would be this. Actually, this is a better way of writing. Not this. I wouldn't maybe even do this. Okay. Plot this as a function of x, and then once you have done, you multiply this function by x. That will give you f of x. Any questions on this distinction between population growth rate and per capita growth rate? Now the second thing. This is again a concept we have discussed. The idea of density dependence, right? This is very widely used. Density dependent growth. Okay, so now what is it? Again, how do we know whether a population has density dependent growth or density independent growth? To do this, always plot per capita growth rate, because the density dependence is defined for the per capita growth rate. That means if the individual, what is the individual growth as a function of population size? If this is a constant, we have density independent growth. If it is a declining function, this would be negative density dependent. And you can have, of course, more complex forms. Okay, and those will be more general density dependent functions. Okay. Instead, if you were to now plot just the entire f as a function of x, how will the density independent look like? Remember that f of x is nothing but this function multiplied by x. A constant function will become now a linear function. So this will be density independent. This is something a lot of students get confused. So density independent growth, if you were to plot for the population, will look like a linear curve. And it is the density independent growth that also leads to exponential growth. Okay. It's a density independent that has density dependent ones that have other forms. Okay. So let me know if you have any questions before we move forward. Okay, so if there are no questions, we'll give you the assignment for today. So here is the lab assignment for today. Okay, here is a scenario. Consider a population which satisfies this dn by dt is equal to Rn times 1 minus n over k, which is continuous time logistic population model. Is it fine? With R0 greater than 0. So there is some population that satisfies this model, okay? And it is currently, let us say, in equilibrium, and that particular point is not very important, okay? Assume that there is another population, okay, who we call, there are many different names one can give. Let's call them harvesters. These harvesters, for example, can be, cattle, sheep on grass, or it could be even humans, sort of, who want to, harvest fish. So, for example, if n represents fish population in a huge lake, let us say, where it follows a logistic population model, let us say we have now introduced harvesters who are humans who will go on try to catch them. Or on the other hand, imagine, there is a natural grass population, and then there are these cattle and sheep who will go and graze the grass. So these are possible examples, okay? It's useful to keep these examples in mind when you are writing equations. And now the assignment for you is write a modified model for n dot that incorporates harvesters. Is the question clear?
So do we need to take into account the dynamics of the harvester population?
Up to you. Okay. So maybe do the following. So now the thing is, you can make that decision early on. I will leave it to you whether you want to do it or not. Okay.
Sir, does the survival of the harvesters depend on presence of,
That's a good. So hold it. Let me write down your questions and clarifications. Okay. First, do you consider harvester? What was the question? Sorry, Arshad, I think, right?
Chandan, sir.
Chandan, what was your question?
Does the survival of the harvester exclusively depend on the presence of grass or fish?
Exclusively on, right? On n, the species that makes up n, up to you. Okay, so you can, this is a very good question. So you can consider two possible assumptions. You can assume that this is one of the many resources available to harvesters. That's one assumption. The alternative assumption is this is the only resource available to harvesters. Entirely up to you. You can make either of the assumptions. Second question that people asked was, do you consider, again, the dynamics of harvester population, right? Is effectively, harvester numbers may also increase or decrease with time, right? Do you consider, again, there are two possibilities. You can assume that the harvester numbers remain same. Alternatively, you can assume their numbers change with time. Again, up to you. But remember that, you're adding, I'm happy with the simpler model. So if you do add, if you assume that harvester numbers change with time, your model will now be more complex, but the choice is up to you. Is that fine? So write the assumptions and then write the equations. So your task is make your own assumptions. List them very clearly. About harvesters and those who are harvested, and then write the model. You do not need to solve the model. I just want you to write the model. Okay. But I do want one condition to be satisfied. In the limit of no harvesters, I want to get back this equation. Is that fine? That's your starting point, no? In the absence of harvesting, you go back to this. Is that fine, people? Any questions? So write down the points. So this is your question. Write both assumptions and the model, and then all assumptions are entirely up to you. I'm not forcing you one way or the other. So only condition I want to impose is in the limit of we get logistic model for n. Is that fine, people? Can I close this sharing? Okay, so you have 1.5 hours now. I would like all of you to submit by 5 o'clock. There is no need for anything more than that for what I have asked. Is that fine? So can I, if there are no general questions you want to ask, I will start the breakout rooms. So I will not bother you for next 20 minutes. I will start hopping around groups from 3:45 or a bit later after that. Maybe I'll give you half an hour fully, 3:55 onwards. Okay. So I'm going to start now. Open all rooms. Okay. Raghuram, what's your group number? You are unassigned.
9, I guess.